Hello friends, so today we are going to solve the questions from rotational motion and these questions are from the year 2022. Total questions we are going to solve 10 and all these 10 questions are from the mains. And for mains, this is part 1 for the year 2022. First question, it states that a meter scale is balanced on a knife edge at its center when two coins, each of mass 10 gram, are put one on the top of the other at 10 centimeter mark. The scale is found to be balanced at 40 centimeter mark. The mass of the meter scale is found to be x into 10 to the power minus 2 kg. The value of x is. So in this case, we are given that we have a meter scale and that is balanced on a knife edge. And then we are going to put two coins, each of 10 gram, one on the top of one another, and that is 10 centimeter mark of the scale, and that the balance amount is found to be then at 40 centimeter mark. So we can just draw an approximate figure for that. Suppose this is our balance and we are putting two 10 gram coins. Okay. So suppose these are the two coins on the scale, on this meter scale, and the distance is said to be 10 centimeter. So we can just say that this distance is over 10 centimeter, and the balance is now at a 40 centimeter mark. So let us suppose this is our knife edge on which it is balanced. So now the balance is at 40 centimeter mark. So this distance is our 40. And so obviously the distance of this coin from the knife will be our 30. And intuitively we can make a random, you can say, a conclusion can be drawn rather, that this coin, because the entire meter scale is balanced, so the downward direction here we are going to have a certain force, that is our mg. Okay, so that entire meter scale is balanced. Okay, this is the basic, you can say, premise of it. Okay. And this is with respect to our, when we have placed a coin, I should have, okay, let me draw the initial figure also. So initially it says that meter scale is balanced when the knife edge at center. Okay. So therefore initially we can say that the knife edge is exactly at the center and this entire system is in the balance. Okay. And for the sake of convenience, let us say that if we are having 100 centimeter is the total length, then on the either side of this scale we are going to have a 50 centimeter each. Okay. And the scale, let us suppose it starts from the left side and which is mentioned as 0. Same goes for this part also. Okay, so this is a starting part, and secondly, let me say that m is the mass of the scale, capital M rather. So this mass is having a scale of capital M. So let us explain it using some theoretical, and let us say that meter scale length is our 100 centimeter, and initially it is balanced at the center. Initially balances at its center, which is nothing but our 50 centimeter, and therefore we can say from here that its center of mass is at 50 centimeter from our left end. Okay, because left we have taken a 0 centimeter, therefore we can say that our center of mass is at 50 centimeter from left end, and let us assume that the mass of the scale is capital M grams. This was the initial condition, and in the second condition when coins are added, so we are given that 2 coins each of 10 gram, so therefore total mass added will be over 20 gram, and they are placed at 10 centimeter mark. Now because of this, now the bridge balances, or we can say the scale balances at 40 centimeter mark. So from here we can say that our scale balances at 40 centimeter mark. Therefore our new center of mass, you can say that our new center of mass, and this new center of mass is of scale plus coin. It is at 40 centimeter from our left side. from left side, because left side we have taken at 0 centimeter. Okay. And we can write mathematically also that position of center of mass, it can be given as capital M, that's the mass of the scale, multiplied by 50 plus 20 multiplied by 10 and divided by total mass, that is M plus 20, and this center of mass is given as 40 centimeter. Okay. Now we can just solve it for our M. And from here we get that this will be 50 M plus 200 is equal to 40 M, and that will be equal to over 800. And this can be written as 10 M will be equal to our 600, which gives us that the value of M is equal to 60. And in terms of the given format, which is in kilogram, so this is x into 10 to the power minus 2 kg. Therefore, we can write this is in grams, and it can be written as 6 into 10 to the power minus 2 kg, and given to us as x into 10 to the power minus 2 kg. So from here we can say that the value of x is equal to 6. So value of x is our 6. Next question. It states that a flywheel is accelerated uniformly from rest and rotates through 5 radian in first second. The angle rotated by the flywheel in the next second will be. So in this case, we can use the kinematic equation for our angular motion, with initial velocity, angular velocity rather, is 0 because it is rest. So we can write that kinematics equation for angular motion, and it starts from the rest. Therefore we can write that our theta will be, that is our angular displacement, will be equal to over half alpha t square. Okay. And here that is omega naught, which is our initial angular velocity, initial angular velocity is equal to 0. And in first second it's said to be rotating by 5 radian. So we can write that angular acceleration, or we can rather find out alpha by using the given information. Therefore we are given that our theta is our 5 radian and time t is given to us as 1 second. So we substitute it and we get this as equal to 5 is equal to 1 by 2 alpha 1 square. This gives us that the alpha will be 10 radian per second square. Now we are going to find out the total angular displacement with respect to the initial. Okay, that means when time t is equal to 2 seconds, then we can just make adjustment in the calculation. So you can say total angular displacement up to t is equal to 2 seconds. And once again, initial will be 0, and let me call this as theta 1, and then we can call that other one as theta 2. So we can say our theta 2 will be equal to our half alpha, and let us call this as t1, and this is our t2. So this comes as t2 square. So we substitute it, we get this is half multiplied by 10 multiplied by 2. Here 2 and 2 goes away. So we get our theta 2 will be equal to 10 radian. Sorry, this is square. My mistake. 1 second. So this is 2 square. This goes by square, and we get theta will be our 20. Theta 2 rather is our 20 radian. Now we can find out our, you can say, displacement in next t second, that is from 1 to 2 seconds. So we can say angular displacement from t is equal to 1 to t is equal to 2 seconds, which is asked in the question. And we can write that as our theta next will be equal to theta 2 minus theta 1, which comes as our 20 minus 5 is equal to 15 radian. And we can solve the same question. I think, let me put the answer. It is a 15 radian. Option B is correct. Option B is correct. And the same question can be used, can be solved rather, by using, you can say, angular velocity. Okay. So we are having, let us call this as using angular velocity. So let us start with angular velocity at t is equal to 1 second. Angular velocity at t is equal to 1 second. We can write this as our omega 1 is equal to omega naught plus alpha times t. Omega naught is 0. Alpha we already calculated. That is our 0 plus 10 multiplied by 1. So this gives us that our omega 1 is equal to our 10 radian per second. And next we can say angular velocity at t is equal to 2 seconds. Angular velocity at t is equal to 2 seconds. Let us call this as omega 2. Once again, this will be about 0 plus 10 multiplied by 2, giving us 20 radian per second. Now we can find out our, you can say, average angular velocity. Average angular velocity and that is from t is equal to 1 to t is equal to 2 seconds. And you can write this as average, omega average will be equal to omega 1 plus omega 2 divided by 2, and this comes as our 10 plus 20 divided by 2. So we get our omega average is equal to 15 radian per second. Now we can use just our displacement equation with respect to our angular motion. So you can say that displacement in that interval and that displacement that interval we can write, let that be a theta, which will be equal to our omega average and change in time, that is delta t, which is 1. So we get this as 15 multiplied by 1. So once again we get our theta is equal to 15 radian. So both the cases the answer is same. Next question. It states that if a force F 3I plus 4j minus 2k acts on a particle having a position vector 2I plus j plus 2k, then the torque about the origin will be. Okay. So we know the basic formula of the torque, that is a cross product of our position vector, that is our r, and the force. Okay. So we can write that our torque about the origin that is our tau is equal to our r cross f, and r is given to us. R is a position vector, is our 2I plus j plus 2k, and the force is also given to us as 3I plus 4j minus 2k, and we can just find out the cross product. So we get our r cross f, this will be equal to our ijk, and we have this as 2 1 2, and this is our 3 4 and minus 2, and this cross product will be coming as minus 2 and minus 4, giving us minus of 10. So this will be minus 10 of I, and then it will be j will be over minus 4 and minus 6, minus will be over 10 because minus of j, so this will be plus 10 of j, and then we are going to k, that is 8 minus 3, that is our 5, which is our plus 5 of k. Okay. So therefore we can say that our torque will be equal to minus 10 of I plus 10 of j plus 5 of k unit vector. This was quite straightforward, and we are having minus 10 plus 10, that is 5, that is option B is correct. B is correct. Next question. This states that moment of inertia mi of 4 bodies having same mass r and radius 2r as follows. I1, moment of inertia of solid sphere about its diameter. I2, moment of inertia of solid cylinder about its axis. I3, moment of inertia of solid cylinder, I3, moment of inertia of solid circular disc about its diameter. And I4, moment of inertia of a thin circular ring about its diameter. If twice of I2 plus I3 plus I4 is equal to x times I1, then the value of x is. So this is, you can say, directly based on the formula, but we have 4 different bodies here. But they are having same mass as well as their radius. Okay. So first of all, we have I1, which is a solid sphere, and with respect to the diameter. Okay. So we can say that solid sphere and about diameter, which is given to us as I1. So we can say I1 will be equal to 2 by 3, 2 by 5, 2 by 5 m r square. And here in all the cases, let me add this small m. So in all the cases, this small m is equal to capital M, and this radius small r is equal to 2 times r, capital R. This is for all the cases. Now we substitute them and we get this as 2 by 5 m, we have 2r whole square, and this comes as of 8 by 5 mr square. And then we are having our I2 is solid cylinder about its axis. So we have our solid cylinder about its axis, which is given to us as I2, and I2 will be equal to 1 by 2 mr square, which comes as 1 by 2 capital M, and this is 2r whole square, which will be coming as 2 mr square. Next is our I3, which is circular disc, solid circular disc about its diameter. So we are having solid circular disc about its diameter. And that is given to us as I3. So I3 will be equal to 1 by 4, and we have this as mr square, 1 by 4 mr 2r whole square, which gives us mr square. And the fourth body finally is our thin circular ring. Thin circular ring about its diameter. And that is our I4, which is equal to our 1 by 2 small m rather, and r square, which can be written as 1 by 2 mr, and this comes as 2r whole square, and this will be our twice m r square. So we found out our I1, I2, I3 and I4. Now we are going to substitute it in the given equation, and we are given that twice I2 plus I3 plus I4 is equal to x times I1. So mainly we are interested in the left side because the right side is already sorted out. So we can say this will be x times, and our I1 is 8 by 5 mR square. 8 by 5 mR square. And for our left side, this comes as 2, and we have our I2. I2 is our twice mR square plus I3. I3 is our mR square plus I4. I4 is our 2 mR square, will be equal to x 8 by 5 mR square. And here mR square is going to cancel throughout, and we will be left with this will be 2 plus 1, that is 3, and this will be coming as 6 plus 2 is equal to 8x divided by 5, and this comes as 8, and this 8 goes with 8, so we are left with that our x will be equal to 5. So the value of x is our 5. Next question. It states that a thin circular ring of mass m, r radius, is rotating about its axis with a constant angular velocity omega. Two objects each of mass capital M are attached gently to the opposite ends of a diameter of the ring. The ring now rotates with angular velocity. So here we are having two situations. One is without the object and other one is the with object. So we can just draw the basic figure. So this is initial condition in which there are no objects, and it is angular velocity is given to us as omega, and its radius is our capital R and mass is small m. In the second condition, we have the same disk and it is rotating about its axis. Let us suppose now it is omega prime. Radius is still our R, but in addition there are two, you can say, objects which are attached to the diametrically opposite end. Mass is given as capital M, and the disk is itself is having a mass of small m. Okay, so we are supposed to find out this omega prime. So in this case we are going to use our, you can say, conservation of angular momentum, and you can say that our conservation of angular momentum and the angular momentum L, we can say the conservation of angular momentum gives us that our initial angular momentum will be equal to our final angular momentum, and keeping in mind this is our initial and our right side is our final, and this can be further written as our moment of inertia, that is our I initial multiplied by omega angular velocity, and then we have moment of inertia of our final and angular velocity we have assumed as omega prime, which we are going to find out. Mainly we are interested in finding out the moment of inertia, that is our I initial as well as I final. So initial moment of inertia and this is our ring. So we can say from here that our I ring, the general formula is our mR². Therefore we can say our I initial will be equal to mR². And okay, now we can calculate our final moment of inertia. Final moment of inertia, and in the final we are having a ring along with two masses, and the masses are at the opposite end of the diameter. So final moment of inertia will be for the system, and that system consists of a ring plus two masses. Okay. Ring will be same, so we can say that our ring's moment of inertia, that is going to remain our mR². Okay. And we are having two masses, so we can say that for two masses, each mass capital M are located at the edge of the ring. Edge of ring at a distance small r from the center. Therefore, we can say that moment of inertia of mass m at a distance r from axis of rotation, Now in this particular question, we are as such not given the diameter, or we can say radius, of these two objects. So we can assume that these two objects are nothing but the point objects. Okay. If the radius or diameter should have given, then we have to solve this by using a different method. First we are going to find out their moment of inertia about their own axis. Then we can use a parallel axis theorem to shift the axis toward the main axis of rotation, which is at the center of the disk. Therefore, we can write that our moment of inertia of this I mass will be equal to, this is mR². Now we are having two masses, therefore we can write moment of inertia for two masses will be equal to 2 times mr². Therefore, total final moment of inertia, total final moment of inertia, which is our I final, is equal to moment of inertia for the ring plus moment of inertia of our two masses. Therefore, we get our I final will be equal to our mr² plus twice mr², which gives us m plus twice capital M multiplied by r². Now we can use the conservation momentum equation which we have already written. You can say conservation of angular momentum angular momentum, and we have written that our I initial multiplied by omega is equal to I final multiplied by omega prime. We simply substitute that I initial was our mr² multiplied by omega, and our I final is our m plus twice m r² and omega prime. Here this r² and r² cancels out, and we get that our omega prime will be equal to m upon m plus twice m multiplied by omega. So this is our new angular velocity. So we are having this as our m omega, and option number D is correct. Next question. It states that a solid sphere ball is rolling on a frictionless horizontal plane surface about its axis of symmetry. The ratio of rotational kinetic energy of the ball to its total kinetic energy is. So in this case, we are given that it is rolling on a frictionless horizontal plane. So we have to find out the kinetic energy. Okay. So the total kinetic energy is going to have two components. One will be the translational kinetic energy and other will be the rotational kinetic energy. So we can say total kinetic energy. Total kinetic energy, we can call this as kinetic energy total, will be equal to kinetic energy translational plus kinetic energy rotational, and the formula are quite straightforward. So we can write our translational will be equal to over half mv² plus rotational will be equal to over half I omega square, where I is the moment of inertia and our omega is our angular velocity. And we have a solid spherical ball, so we know that the moment of inertia for the ball is our, which is basically a solid sphere, is 2/5 mr square. And we also know that of omega is equal to V upon small r. Therefore, we can write that our kinetic energy total will be equal to our, this comes as half m v square plus half I is our 2/5 mr square, and omega is our V upon r whole square. So this 2 and 2 cancels out, and r square will be going away with the r square. So we are left with that our half m v square plus 1/5 m v square, and 10 will be LCM, so this will be coming as 7/10 mv square. So this is our total kinetic energy. We have to find the ratio of rotational to total kinetic energy. So we can see our ratio is our kinetic energy rotational, and we have our kinetic energy total. And rotational is our 1/5 mv square, and this is 7/10 mv square. mv square cancels out, and this comes as 1/5 multiplied by 7, and this comes as 10. So 10 goes by 2, so this comes as our 2/7. So ratio is 2/7. Option B is correct. Next question. It states that a square root of 34 long radar weighing 10 kg leans on a frictionless wall. Its feet rest on the floor 3 meters away from the wall as shown in the figure. If FF and FW are the reaction force on the floor and the wall, then the ratio of FW to FF will be. A basic figure is given to us. We have a ladder of length square root of 34. So this is square root of 34. And for the sake of convenience, let us say this angle is our theta. Okay. Normal reactions are respectively given to us. So let us assume that this normal reaction is our floor. Okay, so this is our floor, and here we are in normal reaction that will be over because of the wall, and there will be mass force, we can see mg at the center of mass for the ladder, that is the downward direction. Okay. And so let me draw this figure separately also. So we are having mg that will be right at the center of mass in the downward direction. So total length, let us suppose, is our L. So this will be our L/2, and this will be also our L/2. And this angle we have zoomed is our theta. And two forces, this is our FW, and this force is our FF. And in the case of this mg, the perpendicular distance, this distance will be our L/2 cos of theta, and for our FW, the perpendicular distance will be our L sine of theta. Because this entire system is in equilibrium, therefore we can say that the, let us call this as point as O. Okay, so with respect to point O, with respect to point O, the entire system is in equilibrium, therefore we can write that our FW times L sine of theta will be equal to our mg multiplied by L2 cos of theta. And we can, here this L and L cancels out, therefore we get that our FW will be equal to mg by 2, and this comes as cot of theta. Okay, and we need to find out our f of f, so we can just find out the ratio that our f of w divided by f of f. F of w we found out is our mg by 2 cot of theta, and f of f will be equal to our mg square plus we have this as mg by 2 cot of theta and whole square and its square root. So we can take mg out of the bracket, so we get this as mg will be equal to, we will be left with cot by 2 so cot theta divided by 2, and here we are having 1 plus 1 by 4, and this is cot square theta and its square root, and we are given that the length is square root of 34. Okay, and okay, so this is also given to us as 3, so we can easily substitute the values, and we can further simplify it. This can be written as 1 upon 1 plus 4 divided by cot square of theta and its square root. One second. Yes, in the options it should be inclusive of square root in the denominator. Okay. And this we can write that you can just substitute the value directly, and we need a cot of theta, so this will be coming as this will be 34 square plus 34 square is 34, and this will be coming as 3 square, that is 9, and we get this as 34 square minus 34 minus 9, and 34 minus 9 will be giving us 25. Okay, no, not 25, but I need its square root also, so this will be 5. then it will be 5 square, that is 25 plus 9, and that will be giving me 34. Now it's correct. So this will be giving us 3 upon square root of 109. 3 upon option C is correct. Is correct. One second, here I forgot. Yeah, mg goes away. Okay, that does help. Next question. It states that a uniform disk of mass m 4 kg, radius r 10 cm is mounted on a fixed horizontal axis as shown in the figure. A block of mass m 2 kg hangs from a massless cord that is wrapped around the rim of the disk. During the fall of the block, the cord does not slip and there is no friction at the axle. The tension in the cord is, basic figure is given to us. So we are having axle and the this string is wound on this axle, something like this. And the downward direction, it is going to have a mg, and there will be a tension that will be present in the string. Now in this case, it says that there is no slipping, and therefore we can say that the linear acceleration will be equal to the tangential acceleration or disk. Okay, or we can say that our A is equal to alpha times r, where alpha is the angular acceleration. So it is going to rotate in this direction with an alpha, and for the sake of convenience, later on we can say substitute it. We can say it is moving downward with the acceleration of A. So we can say that for no slipping, we can write that our A is equal to alpha times r. So let us first of all discuss the forces on the block, which is our having mass m. So we can say forces on the block. Force in the block. And so we are, for this part we are only interested in the block. So this is our block m, downward will be mg, upward will be tension T, and it is moving in the downward direction with the acceleration of A. So we can write the equation that our mg minus T will be giving us ma, and mass is given to us as 2, and we can take, for the sake of convenience, g let us take as 10. So we can write this will be our 2 multiplied by 10 minus T is equal to 2 times A. Therefore we can write the equation that 20 minus T is equal to 2A. Let us call this equation number 1. Now we come to the rotational dynamics for the disk. Rotational dynamics of disk. for the rotational dynamics, one of the key part will be the moment of inertia. Therefore, we can say that moment of inertia about its central axis, that is our I, is equal to over half mR². We substitute the values, we get I is equal to our half mass is 4, this is 0.1 whole square, which gives us that our I is equal to 0.02 kg meter square. Now, if we draw you can see the disk and the tension in the string is going to act as a, you can say, as a tangential force. Okay, so tension acts as a tangential force, and the radius, which is given to us as capital R. So because of this, the tension T is going to generate a torque on the rotating disk. So first part was our moment of inertia, and the second part will be our torque. And we can say tension T acts tangentially and therefore we can say torque tau will be equal to the force and the perpendicular distance about the center. It is going to rotate about the center. And also we can say that our angular acceleration, it is going to rotate with the angular acceleration of alpha. Therefore, we can say the angular acceleration which is our alpha. So based on this, we can also write our tau is equal to I times alpha, and tau is our TR. So from here we can write a T multiplied by R is equal to I times alpha, and we already know alpha is equal to our linear is our A is equal to alpha times R. Therefore, we can write the equation that the tension multiplied by radius R is equal to moment of inertia, and this is alpha times, sorry, not alpha, but A divided by R. And from here we can say our tension T is equal to I times A divided by R². We already know the respective values, so we can say that our moment of inertia we calculated is 0.02 multiplied by A radius is given to us, that is our 0.1 raised to power whole square. So we get from here that tension T is equal to 2 times A. Let us call this as equation number 2. Now we are going to use equation 1 and 2. So we can say from equation 1 and 2, we can write that our 20 minus T is equal to 2A. So from here we get our 20 minus 2A is equal to 2A, which gives us 20 is equal to 4A A is equal to 5 meter per second square, and we are supposed to find out the tension in the cord. So we can just say that tension T will be equal to 2 times 5, which is our 10 Newton. Tension in the cord is our 10 Newton. Next question. It states that a spherical shell of 1 kg mass and radius r is rolling with angular speed omega on a horizontal plane as shown in the figure. The magnitude of angular momentum of the shell about the origin O is aR² divided by 3. The value of A will be. Basic figure is given to us. We have a shell, spherical shell, moving with a, you can say, rolling with the angular velocity omega, and radius is r. So let us assume that its linear velocity is our v. So we can just write the relationship that for rolling motion, v is equal to omega times r. This is standard relationship. Okay. And we need to find out our angular momentum, and for that, first of all, we are required to find out the moment of inertia. Therefore, we can say that moment of inertia of spherical shell that is I is equal to 2 by 3, and mass is m and r is radius square, and mass, everything is given to us, so we simply substitute them with, we get I is equal to 2 by 3, mass is our 1 kg, and our radius is our r square. So this comes as 2 by 3 r square. Now we are interested in our angular momentum. Now here, or let me write it as total angular momentum. Now this total angular momentum is about the origin O. It will be consisting of rotational as well as the translational angular momentum. So this total angular momentum will be our rotational about the center of mass, and it will be also our translational about, that is our center of mass motion relative to O. Translational due to center of mass motion with respect to point O. Okay. And we can say, let us suppose that r is the radius, okay, and let us suppose the point of contact at any given moment of time is at a distance of x from the origin. Therefore, the coordinate of the center of mass can be written as x comma r, because it is a height of r with respect to this x-axis. So, and okay, and this point of contact, let us call this as P. So the coordinate of P will be over x comma 0, and point O, let us call this as origin, and this is 0 comma 0. Therefore, we can say that this center of mass of this sphere, let us call this as O prime. So we considered that our origin O it is having a coordinate of 0 comma 0, and point of contact that is our P, it is our x comma 0, and the center of mass of our sphere, center of mass of sphere shell, we can say that is equal to our x comma r, and that we have taken as O prime. So first of all, let us discuss about our rotational angular momentum. Rotational angular momentum, and it is rotating about, you can say, in xy plane basically. So the axis of rotation will be along, you can say, z axis, which is perpendicular to this plane. So we can say that our angular velocity omega is about the axis through the center. Through the center and perpendicular to xy plane, or which we can say simply our z axis. And for rolling is in the figure, it is given towards the right side. Therefore, we can say that our angular velocity omega will be equal to our minus omega k unit vector. Okay. Therefore, from here we can write that our angular momentum rotational will be equal to I multiplied by our angular velocity omega. I is a moment of inertia, that is 2 by 3 mr square, and this comes as minus omega k unit vector. Therefore, we can say that our angular momentum rotational will be equal to minus 2 by 3 r²ω k unit vector. So this is our angular momentum rotational. Now we come to our translational part. That is our translational angular momentum. Translational angular momentum. So we know that, or we just said that the center of mass moves with the velocity v. So we can say the center of mass velocity is towards our right side. So this comes as y I unit vector, and in terms of our angular we can write this as omega r multiplied by I unit vector. And position vector, for the sake of convenience, let us assume that this our x is equal to d. Therefore we can write this as d comma r, just in order to differentiate between x and y axis. Otherwise it doesn't hold much of the significance. Therefore we can say that position of center of mass relative to the origin O, whose coordinates are our 0, 0, is r vector will be equal to our d of I plus r of j. Therefore angular momentum translational, that is our L translational, will be equal to our r cross momentum p, which comes as our r cross m v. And so we already know this comes as our r cross, and we are having this as omega r times I unit vector. And now we substitute our r unit vector, sorry, not r unit vector, r position vector. This comes as our di plus rj cross omega r, and this is our I unit vector. And this will be our d I cross I, which will be coming as 0, and we have then j cross I, which will be coming as k, and it will be minus of k. So this comes as our minus r square, and we have this is omega k unit vector. Therefore total angular momentum let us call this as L. Then this L will be equal to our rotational angular momentum plus translational angular momentum. So we get our angular momentum total is equal to minus 2 by 3 r square omega k unit vector and minus r square omega, and we have this as k unit vector. So this will be our minus 5 by 3 r²ω k unit vector. We are only interested in magnitude. Therefore, we can say its magnitude will be equal to 5/3 r²ω, and which is given to us as aR²ω/3. This is given to us as aR²ω/3, which gives us that the value of A is equal to 5. Option C is correct. Next question. This question we can also solve by using the theorem of parallel axis also. Okay, because rotational part will be same, and the translational part we can just, you can say, with respect to center at 0, r, and that is going to solve us. Which is sometimes also called as a alternative origin. That is also going to help us to get the same result. But in a more traditional way, we can just solve it in this way. Next question. The moment of inertia of a uniform thin rod about the perpendicular axis passing through one end is I1. The same rod is bent into a ring and its moment of inertia about the diameter is I2. If I1 upon I2 is x pi 2/3, then the value of x is. So we have thin rod, and so this is a thin rod about axis through one of its end. The moment of inertia is our I1, and let us suppose L is the length and m is the mass. And moment of inertia of one of end, in this case it is given as I1. Therefore, we can say that our I1 general formula is our 1/3 ml square. And if we do not remember the general formula, we can use theorem of parallel axis also. First of all, we find out through its center, which is 1/12 m by square. Then we parallel axis theorem, we shift, because the shift will be now L/2, and the answer will be coming same. Okay, so then it will be I center plus mass and the distance md square. D is L/2. So we are going to get I1 will be equal to 1/3 ml square. And this ring rod is now bent as a, you can say, ring. Okay. So second case, this is our ring, and let us suppose r is its radius. And so, but the total circumference of this ring will be equal to L. Therefore, we can say that circumference of the ring will be the length of the rod, that is L, and according to the formula we can write this equal to over 2 pi r. So from here we can say that our r is equal to L upon 2 pi. And I2 is given a moment of inertia about its diameter. Okay. So this is our diameter, and this is given as I2. Therefore, we can say that our I2 will be equal to mR². And okay, we have to find out diameter. Yes, 1 second, let me correct it. We are interested in diameter. Therefore, we can write that the diameter will be equal to its half mR². So we can say our I2 will be equal to over half mR². Because we are interested in diameter, we can also find it if required, because we know that the moment of inertia of a disk passing through its center, this we know, and through the other center, because it will be same, then we can use the theorem of perpendicular axis, and with respect to diameter we can easily find out. Okay. So that will be equal to Iz is equal to Ix plus Iy. Ix and Iy will be same, that is 2 of I. Here it is I2. Mass and radius will be same. And now we can easily substitute value of our R, which is our 1 by 2 m, and this comes as our L square divided by 4 pi square. So we get our I2 will be equal to ml square, and this is our 8 pi square. Now we are simply going to find out the ratio, and we can say that our ratio, which is our I1 upon I2, I1 is our 1 by 3 ml square, and our I2 is our ml square upon 8 pi square. And here this ml square cancels out, so this will be coming as 1 by 3 multiplied by 1, and this comes as 8 pi square, and this is said to be given as x pi square by 3. Therefore, we can say that the value of x is equal to 8. So value of x is our 8. So this completes part 1 for all the 10 questions for the year 2022. We are going to do part 2, in which we are going to solve the remaining questions of the 2022 mains. Okay, this is only of the mains, part 1 as well as part 2. For the advanced, we have already completed the advanced questions of this year 2022. Thank you.